In this lecture, we will be discussing about the edge coloring in graphs. We have already seen what is meant by a vertex coloring. So now here, what we will be doing is we will be giving colors to the edges. So that is called as an edge coloring. But what type of coloring we give has to be defined properly. So that is the first part here. Before giving the definition of the edge coloring, let me recall one important definition which we will be using in the coloring concepts. Okay. So in this case, the first thing that you have to remember is two edges E and F are said to be adjacent. They are said to be adjacent if they are incident with a common vertex. Okay. So if two edges are incident with a common vertex, we say that the two edges are adjacent. Okay, so this is the first thing that you have to remember. So if you have like this will be edge F, this will be edge E, this is incident with a common vertex X. So E and F are adjacent. But if you take a graph like this, okay, it will not be adjacent. Okay. Say for example, if you take a graph like this, we name the vertices as X, Y, Z, W, and I call this edge as E and this edge as F. So for this graph, E and F are not adjacent. Okay. So here it is because E and F are not incident with a common vertex. So in this case, we say that E and F are non-adjacent. So you have to remember this. And now we give the definition of edge coloring. Okay, what is meant by an edge coloring? We paint the edges of graph G. Okay, we paint the edges of graph G such that no two adjacent vertices, okay, no two adjacent edges receive the same color. Okay, so adjacent vertices are given the different colors. No two adjacent vertices receive the same color. Okay. For example, if you take this graph, let me name this vertices as A, B, C and D. So suppose if I give C1 here, color C1 to AB, I cannot give color C1 to the edge AC as well as AD. So I have to give two new colors, C2 and here I should have C3. And now when you look at this BC, I cannot give the colors C1 and C3 because edge BC is adjacent to AC as plus AB. So I can give another color, or I say for example I give you C2. Okay, so now if you look at this, the adjacent edges are receiving different colors. And similarly here with respect to the edge CD, you have CD adjacent to AD as well as AC. So you cannot give CD with color C3 and C2, so I can give C1. So here if you look at this, I have given a coloring. This coloring is called as a proper coloring. proper coloring implies that the adjacent adjacent edges do not receive, okay, do not receive the same color, okay. So no two adjacent vertices receive the same color, all these things are same. So this is called as an edge coloring. Now if you look at this edge coloring, it partitions the edges set. For example, what I do is I write the edges which are colored C1 in one group, and then I write the edges which are colored C2 in other group, AD as well as BC, and I have separately another edge AC. Okay, so in this case, if you look at this, the edge coloring partitions the edge set. Okay, you all know what is meant by a partition. Okay, see, let me again give you this definition. Partition of a set. Okay, what is that? Partition of a set. You take A as a set. Let A be a set. Okay, let A be a set. Now what you do is, you take A1, A2, A3, so on, AN subsets of A such that this condition is satisfied. These conditions are satisfied. Number 1, union of AI, I is equal to 1 to N is A. Then the second one, AI intersection AJ is empty. Okay, this will be the definition. See, in this case, you will have like this. This is the set A. You will have a partition like this. This would be A1, this would be A2, this would be AN. Pairwise, they are disjoint. And when I count all the elements in the subset, that would give you the set A. Similarly, here, if you can look at this for the same graph which I have drawn earlier, A, B, C, D. Okay, suppose if I give C1 here, C2 here, C2 can be given here, C3 can be given here, this one can be given C2. So in this case, your edge set can be partitioned like this: A, B, C, D. Then the second subset would be AD, BC, and the third element is AC. Okay, so this partitions the given set. Okay, and this is also called as the edge chromatic partition. Okay, edge chromatic partition. So what is an edge chromatic partition? A partition of the edge set into independent sets. So this is also called as edge independent set. Okay, this AB comma CD is an edge independent set. What is this edge independent set? The edges AD, AB and CD are not adjacent. You can see that AB and CD do not have a vertex in common. So it is also called as an edge independent set. So this edge coloring gives a partition of the edge set, what you call it as the edge chromatic partition. So here I have taken pains to see to that I have a minimum number of coloring. Okay, suppose here in this graph that is given here, I have 5 edges. I can use all the 5 colors, different colors, so that I need not worry about this. Every partition will have a single set. So in this case, what we will be doing is, we will be minimizing. Okay, is that clear? We will be minimizing the number of colors. Okay, so that will be the main aim. Okay, so we introduce an optimization problem. Okay, problem. What is this optimization problem? Minimum number of colors, minimum number of colors to be used, minimum number of colors to be used to paint the edges, paint the edges of the graph, edges of the graph, such that no two adjacent edges receive the same color. Okay, they should not receive the same color. Okay, so in this case, you are finding out the minimum number of colors. Okay, and this minimum number of colors is called as the edge chromatic number. Okay, so minimum number of colors, okay, that is called as the edge chromatic number. Okay, you will have like this: minimum number of colors is called edge chromatic number. Okay, that is called as the edge chromatic number, or it is also called as the edge coloring number. Okay, you can call it anyway, edge chromatic number or edge coloring number. How do you denote it? And is denoted by, okay, and how do you denote it? And is denoted by chi dash of G, and is denoted by chi dash of G. So in this case, what happens here is that the minimum number of colors will be called as the edge chromatic number, and that will be denoted by chi dash of G. So here what we will be doing is, we will be discussing about the methods to find the minimum number of colors that we will be using in the graphs. So we will begin with certain examples. Okay, first I will give you certain examples of finding out the minimum number of colors to be used, or the edge chromatic number. Okay, so now let me take certain examples here. Okay, certain examples here. What we will do is, you consider this graph. Consider the house graph. Okay, this house graph, let me write like this: A, B, C, D, E. Okay, so now what I do is, I'll first give a chromatic partition. Okay, I give C1 here, I give color C2 here, here I give color C3. Okay, I can give color C2 here, and here I can also give C3. Okay, and now if you look at this particular graph, okay, sorry, this particular edge AE, the vertex E is incident with 3 edges, and 2 edges are colored C2 and C3. So I have a chance of painting C1. But unfortunately, this vertex A1A is incident with an edge which is colored C1. So I cannot give C1, C2, C3. I cannot give C1, C2, C3 here. So I have to necessarily give another color namely C4. Okay, so in this case, if you look at this particular graph, this graph requires 4 colors. Okay, 1, 2, when I give you 3, so I'll have another 4 colors. So in this case, what happens here is that, let me write down the edges here, AB, okay, AB alone. And then for C2, I have BE, CD, and for C3, okay, for C3, I will have BC, ED, and AE. Okay, AE is a chromatic partition. Okay, is a chromatic partition. Okay, is a chromatic partition. Or in fact, you can also be specific edge chromatic partition of G. Okay, so in this case, what you can do is you can conclude that chi dash of G is less than or equal to 4. Okay, you cannot say it is equal to 4. I have to show that it is equal to 4. So in this case, you can conclude that chi dash of G is less than or equal to 4. Okay, and this chromatic partition again is not unique. You can have different chromatic partition. Okay, so as I told you, you will not have a unique chromatic partition. Okay, so here you will have like this. Suppose if I give different color structures to the edges, so let me write like this: A, B, C, D. This one is E. Suppose if I give C1, C2, C3 here I will have C3. Here I can give C2. Here I can give C1. So now I am able to get a partition, okay, which is minimum here. See, for example, here I have AB and ED. Okay, AB and ED. And now when I take C2, I will have AE and BC. And when I take C3, I have BE and CD. Okay, so in this case, here I have used only 3 colors. So is an edge coloring. Okay, so you'll have like this. This is an edge coloring or edge chromatic partition. Okay, this is edge chromatic partition, and therefore chi dash of G is less than or equal to 3. Okay, so here you can, if I can use 3 colors, I can also use more than 3 colors, and the maximum number would be the number of edges, that is painting every edge with a single color. So in this case, you have different techniques, but what we are interested in finding out the minimum. And as I told you, I have not written equal to, because even though I have given a chromatic partition, I have written it as less than or equal to. Now I have to argue that it can be equal to 3 and it cannot be greater than 3. So let me again redraw this graph in the next slide and take the same coloring, so that you will have a beautiful answer for this. Okay. Now when I look at this, okay, I have like this. I think I took like this: A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. Okay, and now I add like this: C1, C2, C3. This one was C2, this one was C3, this one was C1. And I add chi dash of G less than or equal to 3. So what was the partition here? AB. Now I add ED, and then I have AE, and I also have BC in this set, and then the last one would be BE as well as BE as well as what shall I say? BE as well as CD. Okay, I have C. Okay, so now I have told you that this is less than or equal to 3. Okay, so now what you do is you look at vertex B. Okay, this vertex B as degree of B is 3. Okay, you know what is meant by degree of B? Okay, number of edges incident at B. Okay, so in this case you have number of edges incident at B. Okay, here degree, that is called as degree. It is represented like this. Degree of B is equal to 3. So in this case, if you look at this, minimum of, okay, I have like this, minimum of 3 colors have to be used. Okay, minimum of 3 colors are to be used, because here if you look at this, I require at least 3 colors C1 because I have 3 edges incident with each. So in this case I have to use minimum of 3 colors. Okay, 3 colors are to be used. Therefore chi dash of G is greater than or equal to 3. Okay, so now I have this chi dash of G greater than or equal to 3, and here I have chi dash of G less than or equal to 3, and from these two I can conclude that chi dash of G is equal to 3. So in this case, if you look at this, I have proved that I have to use minimum of 3 colors, to paint the edges of this particular graph. And now if you look at this, what is the speciality? How did I take this vertex B? And if you look at this particular graph, entire graph, when I count the degrees of all the vertices, I have either 2 or 3. 3 would be maximum. 3 would be maximum, is the maximum here, and therefore your edge chromatic number or your edge coloring number should always be greater than or equal to your delta. Okay, and of course you have a beautiful theorem called as the Weissing's theorem, which states that your chi dash of G would be either delta or delta plus 1 as the case may be. Let me give you this little bit later. So in this case, you have calculated the edge chromatic number of a house graph. This is called as an house graph. Okay. So now I will take another example. Okay, example 2, again to give an explanation about the edge chromatic number. For this I take a different graph. Consider, okay, the graph would be like this. You will have a graph like this. Let me name the vertices. You have A, B, C, D, E, F and G. Okay. So now if you look at this, degree of C is 4. Okay. And therefore chi dash of G would be greater than or equal to 4. Okay. I have easily chosen vertex C because that has got maximum degree. Now what I have to do is I have to just give a coloring using 4 colors. Okay, say for example if I give like this C1, I'll give C1 here, sorry C1 here, I give C2, and here also I give C2. Okay, I give C2. Now I give color C3 here. Okay, I have to give different colors to these two edges, CF and CE. Okay, so in this case I have to give like this. This would be C3. This would give you, this would be given C4. This edge can be given C4. This edge can be given C3. So in this case I have like this, AB and CG. Okay, these two are given with C1, and C2 is AG and BC. C3 is given to the edges FC as well as DE, and the last color C4 is given to CD and FE. Okay, and this is all undirected graphs, no direction. So you can write CD or DC as the case may be. Okay, is an edge chromatic partition. Is an edge chromatic partition. Okay, so this is an edge chromatic partition, and therefore you have, what is that? You conclude chi dash of G less than or equal to 4. Okay. So now when I combine these two, okay, you know that A less than or equal to B and B is less than or equal to A. You will have A is equal to B. Hence, you have chi dash of G to be 4. So in this case, if you look at this, this helps you to find, okay, find the minimum number of colorings in a graph G, and these type of problems can be used in storage problems. Okay, so the technique of edge coloring can be used variety. You would have seen that when you order computers in the onlines, it will be CPU will be separate, monitor will be separate. They will give you certain wires, but you can easily assemble it. How do you assemble it? What you do is you just match the same color and plug the appropriate pins. Okay, similar is the case here. Okay, similar is the case here. So all these coloring concepts are being used in day-to-day applications like storage problems, okay, or monitoring problems. Okay, you can monitor. Okay, if there are two groups, you have to separate those two groups. All those things can be done using the coloring concepts, in particular the edge coloring concepts. So this is the first part. The second part would be, let me move to the one of finding the edge chromatic number of two graphs. Okay, what are they? Cycle and complete graph. Okay, so now what we will do is we will calculate the edge chromatic number of cycle. Okay, you know what is meant by a cycle. Okay, now I'll just give an example here. Okay, I take C4, A, B, C, D. This is C4. I can paint color C1 here. I can paint color C2 here. Here I can, here I can paint C1. Here I will paint C2. Here I will paint C2. So in this case, I have a coloring like this: AB, CD. Okay, and for C2, I have BC and AD. Okay, suppose if I take an odd cycle C5. Okay, how to do it? This will give you. Okay, this will give you this A, B. Okay, now I have C. Then I have D and E. Okay, so in this case, what happens here is that I have this, D, E. Okay, so I can give different colors here. C1, alternatively with C1, C2, C1, C2. Okay, but now I cannot give C1 here because this edge AB is colored C1. So I give a new color, namely C2. So in this case, what happens here is that I have a partition with 3 color classes. Okay, the edges in the partition is called as the color class. I can have three color class here, A, B, C, D. Okay, this is one. The next one would be B, C and E, D. The last one is AE. Okay, AE. And in fact, you can also call this as the color class. Color class. Okay, so in most of the literature, they also use this spelling for color class. Okay, so you can either use this with an U in the middle or you can omit U. Okay, color class. So this is called as the color class. This is another color class. This is another color class. This color class will be called as C3. Second one will be called as C2. The first one will be called as C1. So in this case, you have different types of color classes here. So now the first aim would be to find the edge chromatic number of a cycle. Now if you look at this, for an even cycle, for the even cycle C4, the edge chromatic number was 2. And for an odd cycle C5, the edge chromatic number was 3. What is this odd cycle or even cycle? The number of edges in the cycle. So in this case, what I will do is, now I will state the Weising's theorem. But I will prove this later. What does this Weising's theorem say? In a simple graph, okay, if you take a simple graph, chi dash of G is delta or delta plus 1. Okay, what is this delta? Delta will be the maximum degree. Okay, that will be the maximum degree of the vertices in the graph. Vertices in graph G. Okay, so this will be the value of delta. So it will be either delta or delta plus 1. It will have only two values. In fact, what they do is they also classify like this. Class 1 graphs. What is this class 1 graphs? Chi dash of G is equal to delta. Okay, this is called as class 1 graphs. And then you have class 2 graphs. What is this class 2 graphs? Class 2 graphs is the set of all graphs for which chi dash of G is equal to delta plus 1. Okay, this will be like this. Class 2 graphs are graphs for which delta is chi dash of G is equal to delta or delta plus 1. Okay, so you have like this. Chi dash of G is equal to delta plus 1. Okay, so this edge coloring is divided into two types of graphs. You will have either class 1 graphs or class 2 graphs. What is this class 1 graphs and class 2 graphs? Class 1 graphs and class 2 graphs are nothing but classes which are classified according to the edge chromatic number. If edge coloring number or edge chromatic number is delta, then you call it as class 1 graphs. If the edge chromatic number is delta plus 1, you call it as the type 2 graphs. So in this case, you remember this theorem. Of course, I will prove this later, and I will be using this to find the edge chromatic number of a cycle. Okay, so now what I do is I take let n be even number. Okay, so what we will be doing is we will be calculating the edge chromatic number for cycle C4, C6 and so on. Okay, so this will be the first step. Okay, what will be the first step? That is, I find the edge chromatic number for an even cycle. Okay, so now let me name the vertices. Let the vertices be labeled V1, V2, so on, Vn. Okay, and of course here n is even. Okay, so now what I do is, you will have n edges. Okay, yeah, because it is a cycle. When you have n vertices, you will have n edges. So now what I will do is, I will alternatively place the colors V1, V2. Okay, and for the second partition, I will give V2, V3. And now here I will have V3, V4. Here I will have V4, V5. Okay, so on. Here also so on. The last one would be Vn minus 2, Vn minus 1. And here I will have Vn minus 1, Vn. Okay, so is a chromatic partition. This will be a chromatic partition. Okay, so this is a chromatic partition. Okay, so I have like this is a chromatic partition. Okay, this is a chromatic partition, and therefore you will have, okay, is a chromatic partition. Therefore chi dash of G is less than or equal to 2. Okay, so in this case what happens here is that you don't have any problem in finding out this inequality, because what you have to do is, you have to just give a chromatic partition, each chromatic partition of the graph G. So now if you look at this particular example, okay, so now I will take a larger one. Okay, C6, you can see that, so I'll name it as V1, V2, V3, V4, V5, V6. Okay, so now you can see that you have 6 edges. This is colored C1, this is colored C2, this is colored C1, this is colored C2, this is colored C1, this is colored C2. That is what I have written it in the general form. Okay, and by Weising's theorem, okay, by Weising's theorem, okay, what does this Weising's theorem do? By Weising's theorem, chi dash of G is greater than or equal to 2. Okay, so in this case, is not greater than or equal to 2, it is greater than or equal to delta. And here in a cycle, here in G is equal to Cn, delta is equal to 2. Therefore, okay, so you have like this. Therefore, what happens to this? Chi dash of G is greater than or equal to 2. And when I combine these two, I get chi dash of G is equal to 2. Okay, so now what I have done is I have just combined these two to get the required answer. So in this case, I have completed this for n is even. Now I have n is odd. N is odd. Okay. So now what happens here is that you have the vertices V1, V2, so on, Vn be the vertices in cycle. In the cycle. Okay. So now what I do is, I take this vertices. Let V1, V2 be the vertices in the cycle. So now what I have to do is, I will have the same concept here. Okay, I'll take like this. Okay, so now what I have to do is, I have to say that the edge chromatic number is 3. Okay, let me write like this, V1. Okay, so I have the label like this, V1. The next one would be V2. Okay, this one would be, this one would be V2, this one would be V3, this one would be V4, this one is V5. Okay, so I have V1, V2, V3, V5. Now what I do is, I give a chromatic partition V1, V2, next one would be V2, V3, then I have V3, V4, V4, V5, okay, so on, okay, here also so on, and I will have another one, namely Vn minus 1 Vn, separate Vn minus 1 Vn, and here I will have Vn minus Vn minus 1 Vn, so I will have Vn minus 2 Vn minus 1, here I will have Vn minus 3 Vn minus 2. Okay, so this is a chromatic partition, therefore chi dash of G, okay, so you have chi dash of G is equal to, okay, what is this chi dash of G? Chi dash of G would be 3, okay, so in this case you have this to be 3, okay, so now in the first instance you have proved that chi dash of G is less than or equal to 3, okay, so that point you have to understand. And now when I use the Weissing's theorem, I will have chi dash greater than or equal to delta. But when I have this chi dash greater than or equal to delta, so in this case what happens here is that I have a problem because delta is 2, but here I have to show that chi dash of G is greater than or equal to 3, okay, greater than or equal to 3. And now what happens here is that, okay, when you look at the color class, okay, now you will have like this is greater than or equal to 3, okay, and now if you look at this edges, okay, the edges here you have like this odd number of edges, okay, so in this case when I take odd number of edges, I have to see to that the coloring is 3, okay, so now what happens here is that each color class, okay, we write like this, the number of edges in the cycle, okay, which is odd, is an odd number, okay, it is an odd number, okay, let me call cardinality of E as small e, okay, so I'll have E minus 1 is an even number, okay, so E minus 1 by 2 will be the number of edges in one color class, okay, so maximum you will have E minus 1 number of edges in one color class. And now when I just count the number of edges, I will have like this E minus 1 by 2 plus E minus 1 by 2, this will give you E minus 1, okay, so one edge has to be given with an extra color, okay, this has to be given with an extra color, so chi dash of G is greater than or equal to 3. So now what you do is you conclude, hence chi dash of G is equal to 3. So let me write down this result, chi dash of Cn, this will be 2 if n is even and 3 when n is odd, okay, so you have to remember this particular result. Okay, so in this case, this is very important. The technique of the proof is important. Okay. So now, before proceeding into the next problem, I will give you certain examples. Okay, I will give you certain examples of finding out the edge chromatic number as we had done for a cycle. Now I will take another example, what you call it as the complete bipartite graph. And for this complete bipartite graph, let me find the edge chromatic number. Okay, so now I will take a simple one, complete bipartite graph. Okay, what is this complete bipartite graph? You know, the bipartite graph, you have a partition of 2, right? You have a partition of 2 sets. Okay, vertex set is partitioned to 2 sets. One vertex is adjacent to the remaining vertices, like this. So this is a complete bipartite graph K33. So now what we will be doing is, we will find the edge coloring number of a complete bipartite graph. First I will find the complete edge coloring number of a complete bipartite graph K33. Okay, so which is given here K33. Okay, let me write like this, K33. Okay, so now what I will do is, I can give 2 colors, C1, C2, C3. Okay, here C1 is already fixed. Let me write like this. C1 has been used. Here I have used C2. Here I have used C3. Okay, this is with respect to this. So now for BD, okay, I give C2, and for BE I give C3, and for CF I give C1. Okay, so now what happens here is that this coloring you get from edges in A, or edges incident in A. It has to be more specific. Edges incident with A, and similarly edges, okay, incident with B. The third one, I have to give a different coloring. So for the edges incident with C, okay, this would give you C3, C1 and C2. So now when I do it, you can see that the colors are different for the adjacent edges. Okay, so D is incident with 3 edges, and these edges are colored C1, C2, C3 accordingly. Here C2, C3, C1. Here C3, C1, C2. So in this case, you can say that chi dash of G is less than or equal to 3. Okay, and by Weissing's theorem, chi dash of G is greater than or equal to delta. Here the maximum delta is 3. So this is greater than or equal to 3. From that you can conclude that chi dash of G is equal to 3. Okay, so now what you have to do is, this is for a complete bipartite graph K33. So now let me generalize this result. Okay, generalize this result. The result would be like this. What is chi dash of K m comma n? Okay, so now this will be minimum of, okay, sorry, not, maximum of, you will have like this, maximum of, okay, what is that? You will have maximum of m comma n. Okay, because you are going to have the maximum degree, maximum of m comma n. Okay, so now by Weissing's theorem, chi dash of G is greater than or equal to delta, and this would be maximum of m comma n. Okay, because here you have m vertices in one partition, n vertices in another partition. Okay, so you have to select the maximum of this. So in this case, delta will be greater than or equal to maximum of this. Okay, and now what you can do is paint the vertices. Okay, paint the vertices in paint the vertices, sorry, not paint the vertices, paint the edges incident with one, incident with one, what shall I say, incident with one vertex. Okay, so now what happens here is that you have to paint the edges incident with one vertex. Okay, so now what happens here is that with one vertex. Okay, so when I paint this, if you look at this, each or edges incident with a vertex is maximum of m comma n. Okay, suppose if I have like this 3 here, and if I have 2, you can have like this. Here I have 3, so I'll have 3 edges incident here, 3 edges incident here. Okay, so edges incident with a vertex. Okay, in fact, you can be more specific. In one partition, is maximum of m comma n. Okay, say when I fix this as m. Okay, say m. Okay, so now what happens here is that I have to give an m coloring. Okay, m coloring here. So each color class I'll have like this. Okay, let me write like this to be more appropriate. Okay, now what you do is to write like this. Say if you look at this, I have like this, see 1, 2, 3, 4. Here I have 1, 2, 3. So now what I do is I take like this 1, 1, 1. Okay, here also 1, 1, 1, 1, 1, 1. Okay, here I have 1, 1, 1. Okay, so now you take this particular vertex x. So you give 4 colors like this, C1, C2, C3, C4. Okay, now you take like this, C2, C3, C4, C1. Next you take C3, C4, C1, C2. Next C4, C4, C1, C2, C3. This would be a maximum coloring. So now if you look at this, each color class will have 4 colors. Okay, each color class will have 4 colors. But anyhow, you can also try this. Okay, you can also say that here you will have like this chi dash of g. It's not coming. Okay, you have like this chi dash of g. I have to show that chi dash of g is less than or equal to maximum of m comma n. Okay, or in other words, what I have to do is I have to just give a chromatic partition. Okay, let me write like this. I will name the edges like this. Okay, in fact you write like this: let the edges, let the vertices in one partition be, okay, one partition be x1, x2, so on, xm, and in another partition, okay, as y1, y2, so on, yn. Okay, I will assume m is less than n. Okay, so now using this technique, I have to just write down the partition. What will be the partition? Let me write it in the next slide. I have this, sorry, I have like this. Okay, so C1, C2, C3, C4 for the first section. C2, C3, C4, C1 for the second section. C3, C4, C1, C2 for the third section. Okay, for the third set of vertices. Edges, and then I'll have C4, C1. Okay, C1, C2, C3. Okay, so now here I will have a partition like this. Let me start with this x1, y1. Okay, first edge x1, y1, and then I will have x. Okay, this is for the second edge, no, c1. Okay, so I'll have x2. Okay, x2, yn. Okay, x2, yn. Okay, so that will be the second set, x2, yn. Okay, x2, yn. So on. Last one would be xn, y2. Okay, so it goes like this. This will be for the first color. Similarly, for the second color, x1, y2, so on, xn, y. In fact, I'll have like this y3. Okay, so on. Last one would be xn. Okay, xn, y1. Okay, xn, yn would be the last one. Okay, so I have to start with this xn, yn. Okay, xn, yn, something like this. xn, yn minus 1, so on. Okay, so this will be this. So you can have chi dash of g is less than or equal to m, which is assumed to be maximum of m comma n. So in this case, for a complete bipartite graph k m comma n, okay, your chi dash of g, okay, chi dash of g would be, okay, that is what you have written here. Chi dash of g is either m or n, which is maximum. Okay, chi dash of g, chi dash of g is maximum of m comma n. Okay, so now what we have done in this lecture, you have to just remember, we had defined edge coloring. The second part is we had understood the concept of edge colorings using certain examples. Then in the third case, we have calculated the edge chromatic number of cycles. Okay, and in fact you can have chi dash of g for cycles, and then chi dash of g for complete bipartite graph. Complete bipartite graph. Okay, and these are the concepts that we had discussed here. Perhaps in the next lecture we will have the edge chromatic number of another important class of graphs, namely the complete graph. So that would form the next lecture. Thank you.